Chapter 7, the last chapter in our textbook, begins with arithmetic and geometric sequences. Now, when you think of a sequence, you think of a list of terms or numbers listed in a specific order. For you and I, it'll be a list of numbers that are written in a specific order. Now, the first kind of sequence that you and I will study and look at is an arithmetic sequence. So, let me give you an example of an arithmetic sequence now. Look at this list of numbers. Now, first of all, each number in the list is separated from the other number with commas. Number two, each number in the list is called a term. So this would be my first term, 3 would be my second term, 5 would be my third term, my fourth term, my fifth term, and so on. Another thing to notice is that this list goes on forever. This sequence is what we call infinite. We know that because of the dot, 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 which means etc. on the end. Now, what makes this sequence arithmetic is that there's a pattern, a specific kind of pattern, though, on how each term is generated. Can you notice the pattern? If you put on your thinking cap, you can see that the pattern is we keep adding 2 to get to the next number. So 1 plus 2 is 3, and then 3 plus 2 is 5, 5 plus 2 is 7, 7 plus 2 is 9. It's the same pattern. If you identify the pattern, then you can continue listing out the terms in the sequence. So do you know what the next number would be in the sequence? Good, 11, and then 13, and then 15, and so forth. The fact that this sequence is generated by adding the same number over and over again, that is, we keep adding 2 over and over again to generate the terms in our sequence, is the reason why this sequence is considered arithmetic. Look at this new sequence here. 3, 1, 8, 4, negative 6, 201, negative 15, etc. Now, this sequence here is not arithmetic. How do I know that? Well, because in order for it to be arithmetic, I would have to keep adding the same number over and over again to generate the terms. And that's simply not true in this case, because in order to go from 3 to 1, you would have to add negative 2. And if you add negative 2 again to 1, you should get negative 1, but you don't, you get 8. So right there I can see that this is not an arithmetic sequence. It is, however, a sequence, but we cannot classify it as arithmetic. And it is an infinite sequence. Now look at this new sequence, 3, 6, 12, 24, etc. We would not classify this as arithmetic because if it were arithmetic, let's see, 3 plus 3 would give me 6, but 6 plus 3 would give me 9, and that's not the next term. So you do not keep adding the same number over and over again to generate these terms. Instead, you're multiplying by something. Do you notice what you're multiplying by? By 2, very good. This first term times 2 gives you 6. This term times 2 gives you 12. 12 times 2 gives you 24. 24 times 2 would be 48. 48 times 2 would be 96, and so forth. All of these terms are generated by taking the previous term and multiplying by 2. Because you keep multiplying by the same number over and over again, namely 2, this is called a geometric sequence. These are the two types of sequences we want to study: arithmetic sequences and geometric sequences. To get us started, though, let us formally define what a sequence is. A sequence is a function whose domain is the set of natural numbers. Let me change that word there. The set of natural numbers. Now, in order to understand this better, we need to introduce special notation. Because a sequence is a function, we will not use function notation, but instead sequences use special notation called subscript notation. Here's a special notation that sequences use. We use subscripts. So a sub 1 would be considered the first term, a sub 2 would be considered the second term, a sub 3 would be considered the third term, etc. And then a sub n would be considered the general term. Now, all of our sequence, the entire sequence, can be described by the general term. And what we can do is input values into n for n, a natural number. We can plug in a natural number for n to find any term within the sequence. Check out this first example. All right, describe the first 5 terms and the 12th term of the following sequences. Here's the first sequence. The whole sequence is described by using a general term. A sub n is equal to 3 times your n value and then plus 2. So what we can do is we can start plugging in values for n to find our first term, second term, third term, fourth term, and fifth term. All right, so a sub 1 would be the first term. So I'm going to plug in 1 for n, and this gives me 5. So we just determined that the first term of the sequence is 5. Let's go for the second term. Now plug in 2. I didn't mean to move the screen there. Now plug in 2 for n. Clean that up. Okay. All right. So this is 6 plus 2, which is 8. We keep on plugging in our n values right here, everybody, in the general term. All right. So the second term is 8. Third term, plug in 3 for n. So this is 9 plus 2, which is 11. Do you notice a pattern with our terms? 5 plus 3 is 8. 8 plus 3 is 11. This sequence does seem to be arithmetic. Let's keep going. Plugging in 4 gives us 12 plus 2, which is 14. And then finally, plugging in 5 would give us 15 plus 2, which is 17. So the first 5 terms of this sequence, now you always list your terms in sequence form. So you have to write your answer like this: 5, 8, 11, 14, 17. So that is our answer for the first 5 terms of the sequence. Now, the next thing they ask for is the 12th term. What I do not recommend, although we could do it theoretically, what I do not recommend is that, you have your first term, second, third, fourth, and fifth term. I do not recommend that you keep on listing out the terms until you get to the 12th term. Instead, why don't we just simply plug in 12 for n, and we can jump all the way straight to the 12th term in this sequence. So it'll be 3 times 12, which is 36, plus 2, which is 38. So the 12th term, and this is how we denote the 12th term, right? A sub 12, the 12th term, is 38. Again, the powerful part of this is that the general term, because the general term was given to you, it allowed you to jump straight to the 12th term without having to list out all of the preceding terms before it. Check out this new sequence. Instead of using a sub n for the name of the sequence, they use c sub n. Doesn't really matter. But the most common names chosen to name a sequence are a sub n, b sub n, and c sub n. All right, so what they want to do, or they want us to do rather, is to find the first 5 terms of the sequence. So c sub 1 would be equal to negative 1 raised to the first power times 1 plus 1. Now notice what we did. Everywhere there was an n, we replaced it with 1 to find the first term. So then this is negative 1 times 2, which is negative 2. So negative 2 is our first term. C sub 2 would be equal to negative 1 squared times 2 plus 1. Be careful when you're plugging in your n values. So it'd be positive 1 times 3, which is positive 3. C sub 3, the third term, negative 1 cubed times 3 plus 1. So now it'll be negative 1 times 4. This is negative 4. Like that. Cool. C sub 4, the fourth term, negative 1 raised to the fourth power times 4 plus 1. So it'll be positive 1 times 5. Positive 5 is the fourth term. Finally, the fifth term, negative 1 raised to the fifth power times 5 plus 1. So it'll be negative 1 times 6. So it'll be negative 6. So then the first 5 terms in our sequence, listed out in order, would be negative 2, comma 3, comma negative 4, comma 5, comma negative 6. Please notice how the signs on the terms are alternating. Negative, positive, negative, positive, negative. This is an example of an alternating sequence. Now, the other thing they wanted us to find was the 12th term. Now, we do not have to list out the 6th term, the 7th term, 8th, 9th, 10th, 11th terms just to get to the 12th term. What we can do is just plug in 12 for n to jump all the way to the 12th term. So that's what you're going to see me do at the moment. All right, so here it comes. C sub 12 is equal to negative 1 raised to the 12th power times 12 plus 1. Now, whenever you raise a negative base to an even power, you get something positive. So then this is positive 1 times 13. So then the 12th term is just 13, positive 13. I can write it out formally. C sub 12 is 13. Very good, guys. So this is just the beginning stages of us working with sequences. Let's go to the next example. Matter of fact, what I would love to do now is, before we go to another example, is to write down for our notes the definition for an arithmetic sequence. An arithmetic sequence is a sequence in which every successive term, each next term, is found by adding a constant called the common difference to the preceding term. In other words, you keep adding the same number over and over again. Let's use this definition to determine whether each of the following sequences is an arithmetic sequence. Now, this sequence is given to you, negative 8, negative 3, 2, 7, 12, etc. Now, they want to know, does this sequence satisfy that definition? In other words, are each of these terms generated or found by adding the same number over and over again? Now, in order to determine that this sequence is truly arithmetic, you have to show that there is a common difference. And one way we can do that is by taking each pair of terms and finding the difference and confirming that the difference is the same. For example, let's check the difference between the second term and the first term. The second term is negative 3. The first term is negative 8. I'm checking the difference between them. So negative 3 plus 8. So the difference between those two terms, negative 8 and negative 3, the difference between them, or if you'd like, consider it the distance between those two numbers. If you're thinking about a number line, the distance between these two numbers, or we call it the difference between the two numbers, is 5. Now, in order for this sequence to be arithmetic, the 5 must be the difference between every single pair of successive terms. So let's check the difference between the third term and the second term. Hopefully it's 5 as well. So the third term is 2, and the second term is negative 3. This would be 2 plus 3, which is 5. The same difference. So far, so good. Let's check the difference between the fourth term and the third term. The fourth term is 7. The third term is 2. and this difference is 5. Very good. Let's check the difference between the fifth term, which is the last term that they've given us, and the fourth term. That's 12 minus 7, which is 5. And this is what I want you to focus on, everybody. 5 is a common difference. Because the difference between every pair of successive terms is the same, we call it a common difference. This sequence is definitely arithmetic. Cool. Let's check out another sequence. All right, 2, 6, 18, 54, etc. Is this arithmetic? All right, in order for this to be arithmetic, the difference must be the same. There must be a common difference. Let's check. A sub 2 minus a sub 1. That is the difference between the second and first term. 6 minus 2. Okay, the difference between the second and first term, or the first term and the second term, is 4. Let's continue. The difference between the third term and the second term. 18 minus 6. 12. Stop right there. No need to continue because we just found that these differences are different. This sequence is not arithmetic. Now, later on in our studies, we'll actually figure out that this sequence is geometric because you keep multiplying by the same number. Look at this. 2 times 3, 6. 6 times 3, 18. 18 times 3, 54. The next number, the next term in the sequence would be 54 times 3. Because you keep multiplying by the same number, you're going to call this later on in our studies geometric. But right now we're focusing on arithmetic sequences. This is not arithmetic. Now, in order for us to work more efficiently with these sequences and to answer some questions about the terms within the sequence, we are going to have to focus on what's called the general term for any arithmetic sequence. The general term for any arithmetic sequence. Now, let's derive the general term for an arithmetic sequence. Because we know their pattern, this shouldn't be too difficult. Now, the first term for an arithmetic sequence is a sub 1, okay, comma. The next term is found by adding the common difference. Let's call the common difference d. The number that you keep adding to get to the next term, let's call that d. So the way you're going to get the second term is by adding d to the first term, all right? Now, in order to get the third term, what you would do is you would now add d to the previous term. So it'd be a sub 1 plus d again. Okay, that's the third term. And I hope you can see a pattern already. In order to get the fourth term, we got to go to the previous term, which is right here, and add another d to it. So a sub 1 plus d plus d plus d, and etc. All right? So I want you to notice the pattern, everybody. So the first term is a sub 1. The second term right here is a sub 1 plus d. The third term, now please notice the pattern. The third term is a sub 1 plus 2d. The fourth term is a sub 1 plus 3d. And I'm going to say etc. So do you see the pattern? This is your first term. This is your second term. This is your third term. This is your fourth term. First pattern I'd like you to notice is that every single term starts the same. A sub 1, A sub 1, A sub 1, A sub 1. The next thing I want you to notice is how many d's each term has. Look at this. This is the fourth term and it has 3 d's. This is the third term and it has 2 d's. This is the second term and it only has 1 d. And this is the first term and it has 0 d's. So each term has n minus 1 number of d's. In other words, 1d less than your n value. Using this as a pattern, we can say that the general term, and this is really important, the general term for an arithmetic sequence, that is to say, all of the terms within an arithmetic sequence can be described as the following. It always starts with a sub 1 plus n minus 1 d. This, everybody, is really, really, really important. If you have anything boxed or highlighted in your notes, make sure it's the general term for an arithmetic sequence. All right, so let's determine the general term for this given sequence. Now, in order to figure out the general term, you need two things. You need to know what your first term is, a sub 1, you need to know what it is, and you need to know what d is, the common difference. All right, so let's go for it. So we can see that the first term, that's the easy part, is 9. It's basically given to you. In order to find d, all you need to do is take any pair of successive terms and subtract one from the other, and it'll show you the common difference. So let's do that. So a sub 2 minus a sub 1. Let's do that. So it'll be 5 minus 9, which is negative 4. Negative 4 is the common difference. You know, you can see that that's true, can't you? If you add negative 4 to 9, you get 5. If you add negative 4 to 5, you get 1. If you add negative 4 to 1, you get negative 3. If you add negative 4 to negative 3, you get negative 7. So we have everything we need to write the general term for this sequence. A sub n is equal to 9, right? I'm following this pattern up here, everybody. So 9, which is the first term, plus n minus 1 times negative 4. Now, all we have to do is simplify. So let's see. Distribute the negative 4, gives you negative 4n plus 4. So then the general term for this sequence can be described as negative 4n plus 13. This is the general term for this sequence. Cool? How about this sequence here that I think we were dealing with this earlier, the general term for this sequence? Now, I'll remind you, since it's off the screen, that the general term for any arithmetic sequence is a sub 1 plus n minus 1 times d. So once again, we need to find two things, a sub 1, the first term, and d, the common difference. Now, the first term is given to you, it's negative 8. To find the common difference, let's take a pair of successive terms. In the previous example, I took the first and second term, but you can take any pair of successive terms. So I'm going to take the, let's see, 1, 2, 3, 4. I'm going to take the last term, which is the fifth term there. Well, it's the last term that's given. A sub 5 minus a sub 4. So I'm going to do 12 minus 7. Oh, okay, the common difference is 5. All right, so let's write down our answer. A sub n is equal to negative 8 plus n minus 1 times 5. When you distribute the 5, you get 5n minus 5. So the general term can be written as a sub n is equal to 5n minus 13. This is the general term for this sequence. Now this one's going to be interesting. Determine the general term for the arithmetic sequence with fifth term 10 and 21st term 58. Now, in order to figure out the general term, you and I are going to have to find two things. So two unknowns. We like to call them two variables, right? The first term of the sequence and the common difference. This time, the first term is not given. And so you and I have to take the given information and figure out how the given information leads us to finding the first term and the common difference. Now notice the first piece of information that's given. The fifth term is 10. That means a sub 5 is 10. And then the 21st term is 58. The 21st term is actually, let me write this underneath it. The 21st term is 58. Now, because this is an arithmetic sequence, they told you that it's arithmetic. That means all of the terms within the sequence must be described like the following. A sub n is equal to a sub 1 plus n minus 1 times d, right? This is the general term for any arithmetic sequence. Because this is arithmetic, all of our terms can be described like this. Taking the first piece of information, 5 here is your n value. 5 is n. So what we can do is plug 5 into n, or n for n, in the general term. The second piece of information says the 21st term is 58. That means we can take 21 and plug it in for n into the general term. So doing this for each of these gives us the following. A sub 5 is equal to the first term, which we do not know, plus 5 minus 1 times d. Now doing this for the 21st term, it would be the 21st term is equal to a sub 1 plus 21 minus 1 times d. Do you see how I plugged in 21 wherever there was an n? Now, what we can do is, on the right side of these equations, we can simplify this. So this is 4d, this is 20d. Furthermore, this notation means the fifth term, and we know that's 10. So I can replace a sub 5 with 10. I can replace the 21st term with 58. And what that would give me, watch this, is 10 is equal to a sub 1 plus 4d, and 58 is equal to a sub 1 plus 20d. Notice what we got. We got a system of two equations in the variables a sub 1 and d. So now all we have to do is solve this system using one of our methods from earlier lessons. How about the elimination method? If I multiply the first equation by negative 1, that would change my system to be negative 10 is equal to negative a sub 1 minus 4d. So that when I add my equations together, my a sub 1 variables cancel, and you're left with 48 is equal to, those cancel, is equal to 16d. When you divide both sides by 16, you find that 48 divided by 16 is 3. The common difference is 3. That's what we needed for the general term. But that's not it. We also needed to know what a sub 1 is. So what we can do at this point is go to one of the equations in your system. How about this one? 10 is equal to a sub 1 plus 4d. That was the first equation within your system. And now just plug d in, which is 3. And you find that a sub 1, after subtracting 12 from both sides, a sub 1 is negative 2. So what I can do is, I can now build my general term because I found the two things I needed, the common difference and the first term. Here we go. A sub n is equal to, here, I'll write down the general term first. So here we go. Ready? I'm going to change the color for us here. So a sub n is equal to the first term, which is negative 2, plus n minus 1 times 3. So now, after I simplify, this gives me a sub n is negative 2 plus 3n minus 3. So the general term is 3n minus 5. Look at that, you guys. That was a lot of fun. So the two pieces of given information gave us a system of equations, and then we solved for the two things we needed, a sub 1 and d. Check out this example. Recall the arithmetic sequence that we looked at earlier, negative 8, negative 3, 2, 7, 12, etc. Find the 96th and 147th terms in the sequence. Now, if I stopped right there, that would be really, really, really tiresome, right? That would be a pain because you and I would have to list out all of the terms all the way until we get to the 96th term and the 147th term. That would take us forever. But if we use the general term that you and I found earlier, we could jump to the 96th term and the 147th term without needing all of the previous terms. So, let's do it. When you say find the 96th term, that means you're going to find a sub 96. Let me make that a look more like an a. There. A sub 96. That's a 96th term. Now, when you say a sub 96, that means you're letting n be 96. So right there, you're going to plug in 96 for n. So it'll be 5 times 96 and then minus 13. So it'll be, let's see, 5 times 6 is 30, carry the 3. 45 plus 3, 48, so 480 minus 13. So then this is 400, let's see, 467. 467 is the 96th term. I'm so thankful for the general term of a sequence, of an arithmetic sequence, is because I don't have to list out all 96 terms in order to get this term. Now, they also want us to find the 147th term. Wow. Okay, so we can do the same process, right? So the 147th term, you're letting n be 147, like this, and then minus 13. All right, 5 times 7 is 35. I'm going to do this multiplication really quickly. Carry the 3. 5 times 4 is 20, plus 3 is 23. Carry the 2. 735 minus 13, maybe, is equal to 722. 722 is the 147th term in this sequence. I mean, isn't that great, you guys? All right, now let's go to another question about this same sequence. Now, the same sequence, but the question now is, what position is the number 602 in this sequence, right? In this sequence here. What position is the number 602 in the sequence? Now, the position that a number or a term has in the sequence is the n value. Remember, a sub 1 means the first term. A sub 2 means the second term. So that subscript is the position that the term has in the sequence. So in this case then, since we're looking for the position, we're looking for n. We don't know what n is. Now, let us not forget that the general term for this sequence we found already to be 5n minus 13. That's going to be our best friend, all right? Now, here we go. We're looking for the we're looking for the position that the number 602 has in the sequence. So we're looking for this n value right here. So all we have to do is plug in the number 602 and solve for n, because that's what we're looking for. All right? Add 13 to both sides. You get 615 is equal to 5n. Divide both sides by 5, and you get n is equal to 123. So 602 is the 123rd term in the sequence. So there's our conclusion right there, everybody. 602. Hey, by the way, notice that 602 is the last term. It's the last term in this sequence. There's no etc. after it. The last term is the 123rd position in the sequence. Last question about the sequence. How many numbers are in the sequence that we were just considering right now? How many numbers are in this sequence? Wait a minute. Didn't we just answer that question, really? Didn't we just figure out that 602, which is the last term in this sequence, is the 123rd position? So if this is the first term, second term, 3 terms, 4 terms, 5 terms, blah, 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 123rd term, that must mean there's 123 terms in the sequence. This is kind of a duplicate question. All right, cool, everybody. So there's 123 terms or numbers in this sequence. Okay, I want to transition our lesson here. Let's start focusing for a few minutes on geometric sequences. Here's the definition for a geometric sequence. A geometric sequence is a sequence in which every successive term is found by multiplying a constant. So not adding anymore, multiplying a constant, called the common ratio. So that number that you keep multiplying by is called a common ratio to the preceding term. Now let's use the definition for a geometric sequence to determine whether each of the following sequences is a geometric sequence. Now, in order for this sequence to be a geometric sequence, you need to be multiplying by a common ratio. So all we need to do to find the common ratio is to divide any pair of successive terms. And then that'll show me what the ratio is between those two terms. For example, if I take the second and the first term and divide them, I get 4 over 1, which is 4. So the ratio of the first and second terms is 4. Now, in order for this to be a geometric sequence, this must be true for every pair of successive terms. So let's check out the third term and the second term. The ratio would be 9 over 4. Wait a minute. These are not the same. These ratios are not the same. 4 and 9/4 are not the same number. So we can conclude right now, there's no need to keep going, that this sequence is not geometric. You know, it is an interesting sequence nevertheless. Do you notice that it is a list of your perfect squares? 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, etc. So it's a cool sequence, but it's not geometric. Let's check out another sequence. Check out this new sequence. 3, 2, 4/3, 8/9, etc. All right, so we have to check the ratio between each pair of successive terms. So let's go. A sub 2 over A sub 1 would be 2 over 3. So the ratio between the second and first term is 2/3. Now let's check the third term and the second term. That would be 4/3 divided by 2. That's the same thing as 4/3 times 1/2, which is, you can cross cancel and you can cross cancel like this. 2 goes into 4 twice, and then you get 2/3. Hey, that's the same ratio that we got earlier, so far this is looking pretty good. Let's keep going though. Fourth term and the third term. That would be 8/9 divided by 4/3. Let's check that ratio. That's the same thing as 8/9 times 3 over 4. Definitely some cross-canceling action going on here. 3 goes into 9 3 times. 4 goes into 8 twice. So that would simplify to 2/3. So guys, look at this. Ratio is 2/3. Ratio is 2/3. Ratio is 2/3. So this is a common ratio. Therefore, this sequence is geometric. All right, pretty cool. Now, in order to study geometric sequences in detail, we're going to have to derive the general term for a geometric sequence. So let's do that now. All right, so go with me here, folks. So The first term in a geometric sequence is a sub 1, comma. The next one will be found by multiplying by your common ratio, call it r. The next term will be found by taking the preceding term and multiplying by r again. The fourth term will be found by taking the preceding term and multiplying by r again, and etc. So the geometric sequence will look like this: a sub 1, comma, a sub 1 times r, comma, a sub 1 r squared, comma, a sub 1 r cubed, comma, etc. So look at this, folks. This is your first term, this is your second term, this is your third term, this is your fourth term, and etc. Notice that every single term starts with the first factor of a sub 1, all of them. Then, notice how many r's you have. This is the fourth term, and you have r to the third power. This is the third term, and then you have r to the second power. This is the second term, and you have r to the first power. This is the first term, and you have r to the 0th power, which is just 1. So therefore, the general term for a geometric sequence can be written as a sub n is equal to a sub 1 times r to the power of n minus 1. This is the general term for a geometric sequence. Again, make sure you have this handy in your notes. Make sure you have this general term highlighted and boxed and ready to use, all right? Now, let us now go to the next example. Okay, guys, determine the general term for this sequence, 2, 6, 18, 54, etc. Now, in order to figure out the general term, you need to know two things. You need to know what the first term is, which they've given us as 2. And you need to know what r is, which is the common ratio. But I just showed you how to find r, right? So let's do this. A sub 1, let's do this. A sub 1 is 2. All right, you need that. Now, r is equal to the ratio of any pair of successive terms. So you can take any pair you want. So like maybe 18 divided by 6. That would be the third term over the second term, right? Which is 3. Now that you know what the first term is and you know what the common ratio is, you can write out your general term. The general term is still on the board. It starts with a sub n is equal to the first term, right? So a sub n is equal to the first term times r, which is 3 to the power of n minus 1. Sometimes books use parentheses just to really be careful here. Instead of the multiplication symbol, they use this, like that. All right? Means the same thing, but I think this is a little nicer, a little more clear as far as what the general term is. All right? Cool. Let's try another. Let's see if we can find the general term for this geometric sequence. All right, now, again, let's notate that we need to find the first term, which is given to us, which is really nice. And then we need the common ratio, all right? So the common ratio can be found by taking any pair of successive terms and dividing them together. Now, I think the easiest thing to do in this case would be taking the second term and dividing it by the first term. So r is 2/3, right? Now, let's write out our general term. Now, it's off the screen, so I'm going to go ahead and write it again for us. This is what we want, all right? So let's plug in what we know now. A sub n, the general term, is 3 times, now the common ratio is 2/3 to the power of n minus 1. This is the general term for this sequence. Check this out. Determine the general term for the geometric sequence with third term 48, sixth term 3072. Now, I don't know if you remember, but earlier we did a problem like this for an arithmetic sequence, and it led us to a system of equations. That's going to be the same kind of thing here. So, let's see if I can walk you through this. The third term is 48. The sixth term is 3,072. Okay? Now, remember that the general term for a geometric sequence looks like this, right? So I can use that pattern to say that the third term being 48 means a sub 3 is equal to a sub 1 times a common ratio of 3 minus 1. Did you catch that right there? They said the third term is 48. When they give me a subscript of 3, that means n is 3. So I'm plugging in 3 for n right here in the general term. That's what I did. Okay, I can do the same thing for the next one. The sixth term is 3,072. The sixth term is 3,072. So we let this n value be 6. So then this is 6 minus 1. Did you catch that? I replace n with 6. All right, cool. Now, let me get this out of the way here. So we used the general term already. Now, this leads us to a system of equations. There will be two things that I do here. Of course, simplify 3 minus 1, which is 2, and 6 minus 1, which is 5. But the third term is 48. So I'm going to replace a sub 3, which represents the third term, with 48. And then the sixth term is 3,072. So I'll replace this notation, which represents the sixth term, with 3,072. That was a tongue twister. All right, so 48 is equal to a sub 1 times r squared. 3,072 is equal to a sub 1 r to the fifth. Now, we have a system here. Now let's be really creative as far as how we solve this. I suggest we use the substitution method. Okay, so I'm going to label this equation 1 and equation 2. All right, so look at equation 1, if you don't mind. This is equation 1, and what I would suggest for us to do here is to isolate or solve for a sub 1. Okay, so we can do that if we divide both sides by r squared. So watch what you get. You would get a sub 1 is equal to 48 over r squared. Now, I'm going to take this expression for a sub 1, and I'm going to plug it into the other equation. The other equation, of course, is equation number 2, which says 3, I guess I'm writing in yellow here, 3,072 is equal to a sub 1 times r to the fifth power. And I'm replacing a sub 1 with this expression, 48 over r squared. So I get 3,072 is equal to 48 over r squared times r to the fifth. Now, don't forget your quotient rule for exponents here. We can simplify r to the fifth divided by r squared if we just subtract the exponents. So 5 minus 2 would leave me with r cubed, right? So this would be 3,072 is equal to 48 r cubed. That was the quotient rule for these exponents, subtracting the exponents. Now, let me move this up a little bit. What we can do now is divide both sides by 48. That would isolate r cubed so that we can solve for r. 3,072 divided by 48, I believe is 64, is r cubed. Now what we can do is take the cube root of both sides, right? The cube root of both sides, so we get r all by itself. And we get r is equal to 4. This is really important. We needed r in order to build our general term. Now, everybody, watch this. All we need now is a sub 1. But now you can come over here and plug in what you just found for r. So let me change the color here. So now a sub 1 is going to be equal to 48 over r squared. A sub 1 will be equal to 48 over 16, which is 3. All right, I found my first term to be 3, and my common ratio is 4. I'm excited. Now we can build the general term. The general term for a geometric sequence is a sub 1 times r to the n minus 1 power. So in this case, it'll be a sub 1 is equal to 3 times 4 raised to the n minus 1. All right, good work, everybody. That's the general term. We did it. Let's go to the last example in this section. Okay, everybody, last example. Recall this geometric sequence, 2, 6, 18, 54, etc. And we found already that it has the general term 2 times 3 to the power n minus 1. What we want to do is find the 8th term in this sequence. All right, to find the 8th term means to find a sub a, that looks more like an a, sub 8. That means you want to let n be 8. So 2 times 3 to the power 8 minus 1. All right, so then this is going to be equal to 2 times 3 to the power of 7. Remember, order of operations says to do exponents first, so you need to figure out what 3 to the 7th power is first, which is 2187. So double that, and you get 4,374. All right, so 4,374 is the 8th term in this sequence. Now, I am super grateful for a general term, right? Because if I did not have that general term, I would have to figure that out by listing out all of the terms up to the 8th term, which would not be a lot of fun. Now, they have some more questions about the sequence. Let me show you that now. Look at this last question. What position is the number 13,122 in this sequence, which ends at 13,122? So when they're asking you what position is this number, they're asking you for the n value. The n value. Remember, the n value gives you the position. Okay, I'm going to start with the general term, which looks like this. And I am going to solve for n. And I'm going to basically let a sub n be 13,122 is equal to the first term, which is 2, times r, which we found to be 3. So there we have it. Now we have to solve for n. Now, to isolate the exponential expression, why don't we divide both sides by 2? That'll get rid of this 2 right here. That one. Okay? So that would simplify things a little bit. That would give us 6,561, I believe, is equal to 3 to the power n minus 1. Now at this point, you got some options. You can either use a logarithm to solve for n, or you can realize that 6,561 is 3 to the 8th power. I like that better, because now that you have common bases, we can set the exponents equal to each other. Add 1 to the left-hand side, and you find that the n value is 9. What does that mean? That means the number 13,122 is the ninth, is in the 9th position in the sequence. All right, cool deal. All right, everybody, this gives us a solid foundation for arithmetic and geometric sequences. I'll catch you in the next lesson.